So already known DFT equation, discrete Fourier transform equation, but you know it. So if I am writing here f of u DFT equals to summation x equal to 0 to n minus 1 f of x e raised to minus j 2 pi u x divided by capital N. This is known equation of the discrete Fourier transform. Already you have studied it. So this you are saying that this is the frequency domain representation f of x. This x is in the time domain. This x f of x you have let's say the f of x equals to one signal 1 2 3 4. It's DFT, very easily you can obtain, and you will get 4 DFT values f of u equal to, and this complex 4 values frequencies. So you have this experience of calculating f of u. So I want to write this equation in a more generalized form. So what I will write it here, say p of u equals to summation x equal to 0 to n minus 1 f of x g of x comma u. Okay, so when you compare these two equations, what you will say that here this f of x as it is I have written it here, this summation sign as it is I have written it here. So for this f of u I have written here t of u, t indication of the transform domain t. Okay, so this is in the transform domain. U, once again this variable related to the frequency you have with you, and for this part say e raised to minus j 2 pi ux by n, what is written here g of x comma u. Okay, here in this DFT equation you have x variable, u variable. X we are using it for the time domain, u you are using it for the frequency domain. Okay. Capital N indicates total number of the samples. So here in the given, let's say example, you have total number of the discrete samples capital N equal to 4. In a frequency domain also you will get 4 different values of the DFT after DFT calculation. Okay, so what now we want to suggest here, we want to discuss here is this e raised to minus j 2 pi ux by capital N. This term is referred as kernel. This term is referred as kernel of this DFT equation. So discrete Fourier transform, in this we have written this, we are saying that this is the kernel. So if you are talking about any other transform, it may be Walsh transform, Hadamard transform, or DCT, discrete cosine transform, where you will find change. You will find change here in the kernel. Kernel is going to change. Okay, so this summation sign will be as it is for the one dimensional signal. This f of x will be as it is. Only the kernel is going to change. That's why what we are writing it here, g of x u, x comma u. This is the kernel part. So in a more generalized equation, this kernel, we want to say generalized term we are writing here. This kernel is made up of the variable, two variables in this one dimensional transformation signal, one dimensional transformation, x and u. These are the two variables. So x is for the input data, input signal, one dimensional signal here you have, and u is, you are saying that transform domain, that is t of u. Here you got it. So try to just concentrate here onto this mathematical equation, because now onwards we are going to use this more generalized form. Okay. Now let's say we want to write the same thing in a, that means inverse discrete Fourier transform domain, IDFT. Using this we will also try to discuss about more generalized equation. So IDFT equation, f of x equals to summation Here prior to that we have multiplication term 1 by n, already you are aware about it. U of 0 to n minus 1, f of u, this is the frequency, and e raised to plus j 2 pi ux by capital N. Okay. Now the more generalized term also we can write it here for this generalize. So f of x, that means in the inverse transformation, generalized equation, f of x equals to summation u equal to 0 to n minus 1 t of u h of x comma. Okay. So now here we got this kernel representation. For this we have written h of x comma u. Okay. T of u is the transform domain signal. Already we have one dimensional signal. So once again what you will say that here kernel is important. This kernel has two variables x and u. When you quickly compare both the equations, that means DFT, IDFT, and generalized equation for both the conditions. So just observe here it is minus sign, and in a transform in the IDFT here we have the plus sign. Okay, this plus sign. Now one more thing, here f of u, whatever you got it, transform domain, for this we have written here t of u. Okay, this notation is very important, and here in a generalized equation we have used notation f of x. Okay, so the representation in a generalized form is very important. So now you know that for the transform domain we are using letter t. Okay. Input data, whatever the input signal we have, for this we are using f, this notation. So using these things, our interest is to write all these terms in a more generalized fashion in a matrix form. Okay. That is our goal. What we will do now, here we will now try to write equation for the two-dimensional generalized equation, because you are very much familiar with now say these terms. Which one? This is generalized equation for one-dimensional signal, generalized equation for one-dimensional signal, right? Now for the two-dimension, T of u comma v summation x equal to 0 to n minus 1 summation y equal to 0 to n minus 1 f of x comma y, and kernel. Now kernel in a general form I am writing it here, g of x comma y comma u comma v. Okay, so it is very in a simple thing what we wrote it. The two-dimensional signal. See the f of xy, two variables are there. That's why it is a two-dimensional signal. F of xy, you can say it is an image, two-dimensional representation in a matrix form. Okay, so these are the pixel values what you have, and its intensity value. We can designate this intensity with this x and y, that is varying. Now the kernel x, y, u, v, these total 4 variables are there now. In a inverse transformation, we can also very easily write it now. F of x comma y equals to summation u equal to 0 to n minus 1 summation v equal to 0 to n minus 1. Here what you will write? Here straightway you can say that I want for this inverse transformation. So t of u comma v and kernel h of x y u v. You got it. So for the two-dimensional signal transformation and inverse transformation very easily you could write it. Okay, now using this logic, using this these two equations, but you are now observing one important thing now we are going to discuss that will help you a lot for computation, that will help you a lot for computations. Okay, so what is the equation? Now I am going to write it in a matrix form. Okay, now in a matrix form, if you want to write a matrix form, let's say for this T, I am denoting it with capital T. Okay. This image, for I am writing here this, what you can say, F. Now what is the next what you can say part? If you want transformation of the image, if you want the transformation of the image, then in a matrix form what we have equation that T equals to A F A. Okay, so this A is nothing but the n by n transformation, symmetrical transformation matrix, symmetrical transformation matrix. This equation is very easy to remember. So you want, our interest is to get the transformation of for the image. Image is here, two-dimensional data. F is the image, two-dimensional data. And for this you want transformation, say you want the Fourier transform or any other transformation, you use this mathematical model where get the two-dimensional data. A is nothing but the its symmetrical transformation matrix. Transformation matrix very easily we can obtain. Okay, and this one thing you have discussed. One more important part after this, what we want to discuss is here. Let's say you want to go for the inverse transformation, that means you want to be in original domain. So what you can do here is very easy. So let's say you have, if B equal to A inverse, A is with you, its inverse, if you calculate inverse transformation, you have B is one term you have with you. So what I am writing here now, B T P equals, I am multiplying to both the sides with this B, and we have this equation A F A. Here also I am multiplying with both the sides B. What happens? So these things are, what you can say, this using this model, we can say, using this mathematical model, what I can write, B T B equals to F. So your interest is for the, let's say, the inverse transformation, or your interest is for the calculation of the F. F is a two-dimensional signal. So you have the transform domain, then the B is nothing but the inverse of A matrix, and you will get it. So these two equations are very important. T equals to AFA and F equals to BTB, where B equals to A inverse. Okay. So we will practice these two equations later, but now you should know that in a more generalized matrix form we can also write in this fashion. So these were the few things related to general representation of this two-dimensional image transforms.